So first up this morning is Keith Packard, future directions for the X Windows system. Now Keith has been developing open source software since '86, focusing on the X Windows system since 1987, designing and implementing large parts of the current implementation. He is currently a principal engineer with Intel's Open Source Technology Center. Keith received a Usenix Lifetime Achievement Award in '99 and sits on the X.org Foundation board. Please welcome Keith.
Good morning. When I put my talk proposal together, of course, that was a long time ago. My talk proposal was about a bunch of changes that other people had been doing and had planned on doing, and a few things I was thinking about discussing, but hadn't actually worked on all that extensively. So, of course, in the intervening 4 months, things have changed, and I did a bunch of different work. So we're going to talk about what I have done, and a lot less about what I'm going to be doing. Although, of course, what I have done always leads to what I will be doing. So what am I going to talk about today? I'm going to talk about a brief history of compositing. Then I'm going to talk about how GL compositing works today and how I want it to work in the future. We'll talk about some of the problems that we're having with the way that we do GL in the X environment today with an extension called DRI2. We're going to talk about how we're going to improve compositing performance and other application performance with where you're replacing a portion of the contents of the screen. And then we'll outline some of the things I want to do with direct rendering. The first thing I wanted to do is introduce you to your enemy. It's always important to know your enemy and understand their weaknesses so you can attack them on all sides. Your enemy is this little device. Anybody know what this device is? Yeah, it's a capacitor. That is the power-sucking monster in your computer. The capacitor represents wires in your computer, transistors in your computer. Anytime you're moving data from one portion of the computer to another, you're fighting capacitance, and capacitance is where you suck all of your power. So my job, and I'll discuss it in the context of compositing. My job is to stop hurting the capacitor and make them go away. You can either try to defeat your enemy or you can run away. And in this particular case, we're going to try to run away. Our enemy is too powerful. So what is X compositing? See, it's where application windows, it's where application contents are drawn off screen. This does a whole bunch of stuff. In particular, when an application makes a small rendering change, it doesn't appear on the screen until somebody decides that the entire screen needs to be repainted. One of the neat side effects of this is the whole application image is always available. So if you want to do those cute little application thumbnails, if you want to do the Alt-Tab stuff where you can see what the application contents of a hidden application would be, you can do that kind of stuff. The application window in this context includes the decorations around the application. How many of you know that the decorations of your window are not painted by your application, but are painted by a different application? Some of you may have used the X window system in the past. So the screen image, of course, the construction of the screen image is just another application activity, right? You take all these images of windows, which could as well be the native video that you're watching, and you glue them all together in some presentation on the screen. Does that presentation have to reflect what the applications think of as the current contents of the screen? Not at all. But often it does, and it's useful when it does. In particular, I don't really care what API you'd use to construct the image on the screen. You can use, in fact, the XComp manager just uses the render extension. You can do the same thing with just copy area. In fact, the internal implementation of automatic compositing, if you turn that on in the X server, XComp manager actually has a little mode where you can turn this on. You can say, don't do the compositing yourself, just have the X server do it. That literally uses copy area. So do you get any fun effects with copy area? Well, you could, but usually not the ones you want. The nice thing about this, of course, is the new screen image is presented atomically, so you can get rid of tearing and partial updates unless you're on Sandy Bridge. UDPates. UDPates. Yeah. Sometimes a spelling checker it's just not a good idea to ignore it. Sometimes it's trying to help you. Okay, here's a picture of how this works. Of course, you have a bunch of window pix maps that are like your GLX gears, the most important application. The other most important application being X logo. GLX gears moves, so it changes on the screen. X logo doesn't move, so it doesn't change on the screen. This gives you your two basic classes of applications, which is why they represent the canonical applications in the world. We used to use X clock as the moving application. I think in the last 25 years, we've really come to a significant technological advance to move from X clock to GLX gears. GLX gears, of course, moves faster. That really is the fundamental change. And of course, so we have this window back buffer, which, as you can see here, doesn't have the window decorations. So the GLX application is actually painting to this window back buffer, and it doesn't have any decorations. And when that application is done with a frame and says, hey, swap buffers, then the X server copies. Anybody know what copying does to our enemy, the capacitor? It makes him very happy. Ooh, lots of capacitance. That's exciting. Copies the contents of that back buffer into the window pix map, which is this off-screen window contents, because it desperately has to get these window decorations around it. So that the window pix map contains the entire contents of the window, the application bits and the window decorations. And then it takes all of those window contents, so we have the X logo, our canonical other application, and GLX gears, and it paints those on top of the root weave and the window back buffer. And then what it does is when it's got the whole next image of the screen put together, it moves that to the front buffer. Now in the ideal world, that motion is just flipping and saying, telling the video hardware, hey, you were displaying this buffer over here. Stop doing that. Display this buffer over here instead. Well, the problem with that, of course, is that if you make a tiny change, like moving the gears in GLX gears, right? If you're gonna have a new frame and you're gonna paint new contents, and you're gonna copy those new contents to a new window pix map and the new window pix map to the back buffer, well, if I want to construct an all-new back buffer for the screen in order to do that tricky page flip thing, then I also have to paint the whole root weave and the X logo as well, because I have to construct a completely new back buffer to flip to it. So the problem here is that you get your choice. You can either do a copy of the GLX gears contents from the back buffer to the front buffer, or you can reconstruct an entirely new back buffer and do a page flip. What we call that page flipping, when you're flipping between the two scan-out buffers. In either case, you're doing a lot of memory manipulations. You're either painting an entirely new image and page flipping, or painting a subset of the image and doing a big copy of the application. Those both kind of suck. X has had external window management for a long time now. X10 had external window management, but X10 was more optimal than X11 because X10 didn't have any ugly window decorations. That whole window decoration problem, not a concern in 1985. In our infinite wisdom, of course, in 1986, 1987, we came up with a new plan to actually let you put fancy window decorations around your windows and and continue to use the external window manager by painting all those ugly window frame contents in a separate application. Now, when you're just doing clipping-based rendering instead of this compositing-based rendering, it really doesn't matter because the application is always painting right to the frame buffer. There's no separate back buffer. So this fact that there's a window manager painting stuff around your application has no performance impact at all. But of course, with compositing, it matters a whole lot. Okay, so what are the limitations of DRI2? One of the big problems we had with DRI2 as soon as we came up with this fine plan is the security guys went bananas. It's like, you've introduced a new namespace with no hooks into the security infrastructure in the kernel. This is awesome. I don't see possibly how this could go well. The global gem handles, gem is the graphics execution manager inside the kernel, and it manages memory and execution resources for your GPU in the kernel. I should have put a lovely slide in about this. How many of you know about gem and the kernel DRI? Yeah, that's what I figured. Inside the kernel, somebody has to manage your graphics card. Your graphics card is like a separate computer. So you basically have to write an operating system for your graphics card. Well, we have Linux, it's a lovely graphics CPU. So we had to construct basically an entirely new management system for your graphics card. It has to manage the two primary resources in a computer, which are time and space. Right? There's 4 dimensions of our reality. In the computer, of course, there are only 2 dimensions because memory is linear. So we only have time and space to manage. Gem manages both of those. It manages memory allocation, which is space, and it manages execution resources, which is time. The way that it manages memory is that it has an allocator. That's how you manage memory in the real world. And so applications come into the kernel and say, hey, allocate me 47 megabytes of graphics memory because I want to paint this really cool image of the Mona Lisa and send it to the moon or something. So the kernel has this lovely pile of memory, and it has to provide a name back to the application so the application can name this piece of graphics memory. Well, when the application is just communicating amongst itself, those names are local. Those names aren't exposed to other applications. But in order to get an image, that lovely back buffer of the GLX gears window, in order to get that image from the application to the X server, you have to pass it through the network protocol that is X. And we can't really pass the giant image. We can only pass little tiny bits. And so what I really want to do is pass a reference to that image. So what we did in GEM is we created these things called global GEM handles. Now, a global GEM handle isn't a reference. It's just a name. And there's a really big difference there. So when you have a name, when you have a reference to an object like an open file descriptor, when you close that, the kernel can go and release resources related to that resource. With a GEM handle, you have no idea who has that reference. You pass this number down, this name around, and any number of applications can know the name. So the kernel has no idea when the last person is done using that object, unless everybody is very carefully remembered to forget the name. That's really the only way the thing goes away. So right now, what we do is the name doesn't hold a reference to the object. So everybody in the entire system, your application, your compositing manager, and your Windows system all have to kind of know what names are in existence and remember to throw them away. So we have this huge distributed memory allocation problem. And the problem, of course, is not so much in forgetting to throw things away, but in throwing things away at the wrong time. If you throw things away at the wrong time, the buffer disappears, and all of a sudden, you can reuse the name, and the name gets reused because they're small integers, and the kernel has a little small integer allocator. So if you throw something away, your name for that, which is just a small number, can now refer to somebody else's object. So if you throw something away and somebody else is about to use it, they can actually go and get somebody else's object. So you can get random contents on the screen. Of course, the other problem with GEM handles is they are GEM handles. They're not some kernel generic object. They're only related to GEM. So in particular, if you want to take memory from your video camera and put it into your environment, there's no way to get a GEM handle to memory from your video camera. Video cameras don't speak GEM. They don't use the GEM API. Inside the kernel, we've created a new infrastructure called the DMA buffs. DMA buff is now a global kernel infrastructure that manages pools of device-specific memory. Device-specific memory. That's a lot like GEM. So a DMA buff now is this global kernel-wide notion of piles of memory, but DMA buffs are referred to by file descriptors. And what do we know about file descriptors in the kernel? File descriptors are not names. File descriptors are references. When you close your file descriptor, the kernel knows that you've closed it. If your application crashes, your file descriptors get automatically closed and all those resources go away automatically. You can take a file descriptor and give it to some other application, to a Unix domain socket. That reference travels to the Unix domain socket, to another application. So you can pass references around. It's awesome. The other problem with DRI2 is that all of the back buffers for your Windows, and other buffers too, but oops, we don't do that. All of these buffers that I'm talking about aren't allocated by your application. They're allocated by the X server. So if your window changes size, the X server reallocates the back buffer. And so your application is happily drawing to this back buffer, putting a bunch of contents in it, and the user goes and resizes your GLX gears because they want to see how slow it goes when it gets bigger, right? The GLX gears, of course, is designed to show you that your application always goes at 60 hertz. And then users complain, why is my GLX gear so slow? It only goes at 60 FPS. Right? That's what GLX gears is for, is to generate bug reports so my graphics card is slow. So that's the user perspective. So the problem with doing stuff on the server side is that it requires a round trip. You want to allocate a buffer, you have to go ask the server. So here I am, I want to draw some stuff and give it to the X server. Well, in order to get the buffer the X server is going to know about, I have to actually ask the X server, can you allocate me a buffer? And the X server asks the kernel for a buffer, then the X server remembers this buffer. Why the heck did we do this kind of insanity? Right? You're asking yourself, why would you have the X server allocate a buffer that the application is going to ping to? Well, that does go back to some very dark history. Imagine the year is 1990 and you're SGI and you're building a multi-core, what?
That was me.
Yeah. It's your fault. Yeah. We'll blame you today. And you're building a multi-core machine that has this amazing GPU in it. And you want to be able to use those multiple cores to draw things simultaneously. And this notion of this thing about threaded programming, that was some newfangled notion. That was scary and researchy in 1990. So what people do is they'd actually write parallel rendering applications using multiple processes. So they're writing an application that wants to draw that two processes are going to collaborate in generating a single frame. So somebody has to allocate the place they're going to render to. Oh, I know, we'll put it in the Windows system. So the GLX protocol actually has all of the shared rendering infrastructure allocation done in the X server so that you can have multiple processes rendering to the same window. Well, it turns out that in the traditional X technique of deprecating bad functionality, what we do to deprecate functionality in X is we break it accidentally. We wait 3 or 4 years, see if we've gotten any bug reports. If we've gotten a bug report, we may actually go fix it. But if we have gotten no bug reports, we silently delete the feature. This has worked awesomely. We've done all kinds of stuff this way. I gave a talk at Plumbers Conference like 5 years ago listing like a dozen places in X where we had accidentally broken something and then felt free to remove it later on. I think the kernel should adopt this plan. And the kernel guys have this horrible policy of never breaking applications, and if any nutso kernel API, however bung hits that API is, if some application could have ever seen it, it can't change. It's a terrible idea. You should just break things randomly, applications don't complain, you're good. I would like to say this is an official policy of the X development environment, but that really is an accident. In any case, we discovered about 6 months ago that this sharing of buffers doesn't actually work anymore. Because we only share the back buffer. We don't share depth buffers or stencil buffers or whatever other buffers you have. So you couldn't actually use this in the current X environment. So we feel free now, because it's been broken for 1.5 years, to delete this feature. The other problem, of course, for this server-side allocation is resize. If your window gets resized, the server immediately resizes, which is to say allocates another back buffer for your window. So if your application happily rendering to a frame and is just about done and you're going to call swap buffers and put that stuff up on the screen and your window gets resized, where did those old back buffer contents go? Ooh, out the window, they're in the bit bucket. Because the new back buffer has nothing in it. And so if you do draw, resize, draw, flip, and then you don't ever do any more drawing again, then your window remains black. It's awesome. The other problem with resize is the way we would tell the application that we were doing a window size is by sending an event to the application. Right? We send an asynchronous thing, which it is. It's a resize. It's kind of an asynchronous operation, telling the application, oh, by the way, your back buffer has changed size. Well, the problem with events is that that's the way the X is modeled, and in fact the way most event-operated systems, somebody has to have a notion of sequentiality, right? You have to do operations in some sequence. And in the X world, we have the application sequencing through the events. The problem with sending an event that the application doesn't know about, because the application doesn't care how GLX is implemented, that's hidden from it. The problem with sending an event is, when do we process that event? We're supposed to process that event when the application understands that the size has been changed. So there's this window resize event, and then there's this DRI back buffer size changed event. So we're supposed to inside the Mesa, the GL implementation, we're supposed to flip buffers exactly when the application has processed that resize event. Do we have any idea when that happens? No, we have no clue. So the whole notion of using events and having them processed secretly by the library just can't work, because the application has no idea what the size of the window is. So oftentimes, for applications that only render a couple of frames and then stop, like say a GL-based terminal emulator or a GL-based web browser that isn't animating constantly, the screen would just go black. So DRI2 is fundamentally broken because of that. The other dimension that we're trying to solve here is compositing. There's so many copies. Our enemy, the capacitor, is very happy. They're winning the battle. Global warming is happening because X compositing is using too much power. There's two modes we can do, and we talked about this a little bit before. You can either do whole frame, where you paint an entirely new scene for the display, and change which buffer you're scanning out from. The lovely thing about this is that you can easily synchronize this to VBlank so you don't get any tearing, which is to say the frame doesn't switch in the middle of your screen. Have you ever seen a movie where you get this weird line effect during motion? Right? That's video tearing. Well, in a composited world, that happens all the time if you do a partial update and you're doing an update, and the update happens right as the retrace beam goes right through it. Now, fortunately, we still have VSync because we have a time when we can switch the whole screen. Unfortunately, we're moving to a world where we're not going to have a VSync anymore. In the new glorious world of lower power displays, we're going to be doing partial updates of the screen. So I don't know what's going to happen then. It's going to be interesting to watch people, because we've had this notion of a VBlank since 1930-some, and that's just going away. The other thing, of course, you can do is a partial frame. It's totally unsynchronized. You're just blasting a new copy of pixels into the frame buffer. We can synchronize that to VBlank. And in fact, in pre-Sandy Bridge Intel hardware, there was actually a little operation that said, if the scan-out beam is in these pixels, then wait until the scan-out beam is not in these pixels. And that was awesome, because we could just put that, I'm going to update these, this little 10 by 10 rectangle. Well, if the scan-out beam is in those 10 scan lines, just wait. A couple microseconds later, the scan-out beam would be below those 10 pixels, and that blit would happen. You see no tearing. It was awesome. Of course, as hardware engineers are wont to do, after Sandy Bridge, they removed that feature from the Intel hardware. So if you've ever watched a video on Intel hardware, Sandy Bridge or Ivy Bridge hardware, if any of you ever noticed the fact that it tears now? Nobody? Yeah. I'm really sorry. I can't fix that. I know. I should wear a shirt. I'm sorry, dude. I can't fix your Windows system. Yeah. Okay. And why isn't this lovely little... There we go. At least there's no tearing here, because actually there's a lot of tearing. You just can't see it, fortunately, because I'm doing an entire screen update, and your eyes can't see the tearing. Motion is the only time you can see it. Okay, so here's how composite full update goes. To do a composite full update, I take the desktop window. Anybody remember what this pattern is? The lovely root weave? You probably can't see it. No, that is just a blur of gray, isn't it? On my monitor here, it's the lovely traditional X root weave. What? Imagine in your mind a little stipple that looks like this. X present. What? Oh, with the moire patterns, absolutely, absolutely. On your color monitors, absolutely. Yeah. Did you have flashbacks? You understand why this pattern exists? This pattern exists so that when you do an XORed vertical or horizontal line, you can still see it on a monochrome screen. That's why this pattern exists. An amazing invention. It's kind of nice to have it, a little historic. You can, of course, run your Xserver with this as your background. It's still very possible in the -retro mode. Inside the Xserver, that mode is actually called Party Like It's 1987. Probably the longest variable name in the Xserver, but one that nobody has any trouble typing or remembering. There's a couple other features like that. It uses can you see the little X cursor?
Yes.
Yeah. Oh, it's fine. You don't actually need to see it. It's just a little bit of nostalgia for those. In any case, you take the desktop window and you take the application pix map, you paint them into an entirely new screen back buffer, and then you change that to be the screen buffer. That's how you do a full update. And it's expensive, right? I'm copying the entire desktop window, which is usually not the root weave, but usually some image, oftentimes including a beach. You guys probably don't need to do that. You've got beaches right outside your windows. For those of us who live far from the tropics, a beach image is usually very restful. Maybe for you, a snowy scene would be restful. I don't know. Freaking hot out there. Give me some snow. So we paint the entire new back buffer and flip it to the front buffer. A pretty simple operation, but you can see I've made our enemy very happy, the capacitors. I flipped a lot of capacitors around to make that happen. And in composite partial update, so say I just say the old back buffer didn't have the L there, the little pink rectangles showing where the update's happening. So it had the outline cursor, and it had a blank space there. So what I'm going to do is I'm going to type L, and the application is going to paint the L, and it's going to paint the new cursor. And that damaged information will toddle off to your compositing manager. The compositing manager will say, whoa, that's a little tiny change. So the compositing manager copies the new that tiny subset of the new application contents into the existing back buffer, right? It's got the old back buffer and the new back buffer, and then it just copies those contents into the front buffer. So I've done 2 tiny copies instead of a giant paint and a swap. So your compositor, of course, has to constantly choose between these 2 modes of operation. The awesome part about GL is that this operation can't be VBlank synchronized. There's no way to do a copy that is synchronized to your VBlank. So if you do a bigger partial update, you get a bunch of tearing. Because the way that you do this with GL is the application isn't using swap buffers anymore. The application is using, copy pixels. And so there's no synchronization available there. There are compositing managers that will put some little kludges in to do a little VBlank synchronization and quickly copy, hoping that it's going to work out okay. Sometimes that works, sometimes it doesn't. Nothing really formal. So what's the plan? This is a working name for this new extension, the DRI 3000 extension. Because something numbered 3000 always solves all the world's ills, right? Or at least destroys the world. It's hard to know which will happen in this case. We're going to try to fix some of the problems in DRI2. We're actually going to try to fix everything we know about. So if you have problems in DRI2, we'll put those fixes into. The other plan is to, instead of using the current gem global handles for this, we're going to use file descriptor passing through the Unix domain sockets to pass DMA buff file descriptors that point to these gem objects. That solves a bunch of referencing problems, solves a bunch of security problems, and also makes it no longer gem specific. Right now the DRI2 specification says there's this magic 32-bit number that you put here that somehow everybody knows is going to refer to your object on both sides of the wire. Not a great specification because magic numbers are often wrong, and magic numbers aren't very well bounded. So with DRI 3000, we'll be able to put a little file descriptor on the wire and say, oh, by the way, that file descriptor you got, that's your buffer. It's a DMA buff handle. You can mmap it. And the other thing that I'm going to talk about in a little while is some page table tricks to reduce copying. Now these page table tricks only work on integrated graphics because that's all I care about. So for DRI 3000, obviously, I don't know what the name will be. We were thinking, could this be a change to DRI2? Could we change the DRI2 protocol? Do we want to create an entirely new protocol? We don't know yet. There's a bunch of experimentation. Probably the right thing to do is to create a new extension so that we can get rid of the old one by breaking it, right? That's the traditional technique. You break the old one and get rid of it eventually. Obviously, we want to allocate the buffers on the client side. What's this going to do to GLX compatibility? Oh, well, it's going to be broken. Well, wait a minute, it's already broken. So it won't actually change that at all. By allocating stuff on the client side, we won't lose application contents on resize. The application will be responsible for telling us what buffer it wants to put on in the window. And if that buffer is the wrong size, well, at least you get what the application did paint, which is exactly what the application should do. The application can come along later, or even during that frame, process a resize event, cause a new buffer to be allocated, and I'll show you how that happens. And then those new contents would show up on the screen the next time. The important thing here is the application is in charge of knowing what size of buffer it's painting. The application is completely in charge of synchronously handling resize within its regular application context. The other awesome part about doing client-side buffer allocations, we can implement this new extension called EGL Buffer Age. This is kind of one of those widgy little GL extensions. What EGL Buffer Age does is when you do a swap buffers, you can say, what are the contents of my back buffer now? Because often, so you have 2 buffers, a front buffer and a back buffer. If I copy the back buffer to the front contents, then the 2 have the same contents. If I swap the 2 buffers, then this buffer has the contents of the previous frame. In both cases, the application can usefully use that information to incrementally update that back buffer for subsequent frames. It's a huge optimization, especially for our favorite application, the compositing manager, which often does very tiny updates to very large buffers. For games, who cares? I'm painting the whole frame again because I moved my stupid HUD again. Whoa! But for my desktop, which is where I spend all of my time and consume all of my power, I very rarely update a significant fraction of the screen. So EGL Buffer Age is going to let us do some small updates on the screen. by telling the compositing manager what its new back buffer contains. We're obviously going to pass stuff by file descriptors using DMA buff. The nice thing about passing stuff by file descriptors is that the socket holds the reference during the transfer. So after I put the file descriptor into the socket and send that down to the kernel, my application can close that file descriptor, knowing that that file descriptor, the reference to that is going to travel through the socket to the other application, be picked up by another file descriptor on the other side, and he'll have a reference. So in particular, when the X server is done with a particular DMA buff object, you just pass that file descriptor back to the application and close the file descriptor, nicely solving the ownership problem. So now I'm going to talk a little bit about window size. I think I have, okay, yeah, this presenter console is not working for me today. Yeah, I've got a slide about that in 2 slides. But the application, so our library is actually going to have to guess what the back buffer size is, unfortunately. There's no API in GL where the application says, oh, my window is this big. Because in the bad old days of when GL was invented, there was only one size, the entire frame buffer. You didn't have this Windows system stuff, newfangled Windows system stuff. So the GL application has never had an API to tell the library how big the window is. Or more importantly to us, how big it thinks the window is. So we'll have to guess. For GL buffer reuse, what we're going to do is after the swap, the application is going to ask the X server, hey, I sent you a bunch of buffers. Are there any of those you're not currently using? Those might be good ones for me to use again. So if you do the swap, then if you just swap 2 buffers, then one of the idle buffers is going to be the previous front buffer. If you did a blit, then you'll just get the previous back buffer. Now the X server is welcome to do whatever kind of swap it wants, whatever is the most efficient. So if you do a swap and then a blit, then you're going to get 2 buffers back, the previous front buffer and the previous back buffer, because both of those are going to be idle now. We're going to take a round trip per frame to get this information, just like DRI2. So we're not going to actually speed up the swapping problem, but the only time this round trip matters, so we're going to take 1 round trip per frame. How many frames do we do every second? We do 60 of those every second. So we're going to take a round trip to the X server 60 times a second. It's a nice place for the X server to say, whoa, slow down, you're doing too many. It's also a nice place for us to get this idle buffer information. It seems to be working okay for DRI2. The only time people complain is when they run our favorite application. What's that application? GLX gears, exactly. GLX gears at this point can only run at like 2,000 frames per second maximum because of that horrible round trip we do. Oh no. So the other thing I'm going to put into this buffer, into this reply, is I'm going to put in a good size for a new buffer. And this good size in the simplistic case is going to contain the current size of the window, right? This way the extension can actually know the current size of the window, at least at that point. And so it can know what a good size to allocate new buffers might be. And now I'm actually going to put a new size, and then I'm going to tell the application, oh, don't draw at the upper left-hand corner. Why don't you put your DL contents just a little bit down from that and clip them a little bit? And I'll show you why we want to do that in a second. So the problem with the GL API is that the GL API contains no information to the driver about how big the window is. On DRI2, the buffers are allocated in the X server. The X server knows all about your window size. And the clients get a nice event when the back buffer is resized. As we talked about, there's a huge number of boundary conditions. It's a disaster. But we don't have any actual information about the window size, so we're going to have to guess. And we're going to use a collection of GL APIs that are going to give us some notion of what the actual window size is. So an application in GL usually needs to set the viewport, so you can get a transformation from usual a -1 to +1 GL region to the window. So you get this viewport transformation. So the application tells us what the current viewport is. And all the GL operations, I hope, there are some exceptions, most of the GL operations are actually clipped to that viewport. So the union of all the viewports you do in a particular scene gives me a really good idea of the region of all the pixels that you've rasterized for a particular scene, right? You just take, if you say set viewport over here and set viewport over here and set viewport down here, if I just draw a box around those, you can't put any pixels outside of those. So that's probably a good approximation of how big the back buffer needs to be. Of course, we're going to get another hint from the X server every time we do the swap. The X server is going to tell us what the size of the buffer should be. So what we're assuming here is the client is watching the configure notify events. Fortunately, we did a little review of the GL protocol, and there's no way for the application to ask GL what we think its window size is, because we think its window size is whatever you told us the window size is. And so if you're telling us the window size that we guessed that we think it is, then we're going to be telling us what you told us last time, and things will not go well. Fortunately, there's no way for the application to ask us what we think the size is. Because after all, in GL, the size is the entire frame buffer. Who needs to know the size? So we're going to assume that the application watches for configure notify events and resets the viewport. And then we're going to just reallocate as needed. So if you set a little viewport down here and you set a little viewport over here, we'll just reallocate the back buffer and do a blit. Now, of course, we'll remember the size from the last frame, so that, you know, the application startup, we may do a few little reallocations, and if you resize the window, we may do a few reallocations. But in the steady state, I think we're going to know what the size is pretty well. Of course, the swap buffer is going to clip. It always does. If the back buffer is too small, it's going to fill the remaining area with the window background. We already have a nice defined pixel there. So if you do a swap buffers and your buffer is smaller than the current size of the window, then we'll swap in your contents in the upper left-hand corner, and we'll paint the rest of the window with a window background. That should work pretty well. Okay, so how are we going to avoid this window manager induced copy? Remember that GLX Gears application, the back buffer was smaller than the stuff with the frame. We had to reallocate. We're going to ask the client to allocate a bigger buffer. Just make it big enough for the decorations and stick the application in the middle of that buffer where it belongs. And then the client is going to tell us where it stuck its application in this buffer. And then we're going to track. And if things are good, if the application has put its contents in the right spot in this buffer, and there's enough space around the outside for the window decorations, we're going to take all the window decorations and just copy them around, kind of draw them around the application. And now we have a window that has the application contents and the window manager contents that we didn't have to copy those application contents. Now the other cool thing is the X server has this lovely damage infrastructure which lets me know when anybody touches any buffer. So we're going to track which buffers, remember, everybody knows all the buffers we're using for this window. We're going to track which have the current image of the window manager frame. So if you give me one frame that has your contents in it, and I've painted the window manager around it, then you swap, and I do it again, and you swap back. Oh, wait a minute, I've already painted the window manager contents in that frame, I don't have to do it again. So I'm not going to copy the window manager contents onto that one. And so I can skip the copy. So in the steady state, the application is going to paint its contents, and I'm done. I don't have to do any additional work. So I should just be able to swap pointers around for the back buffers. And the nice thing, of course, is that I can always fall back to the copy operation. Again, the application is going to know whether I did a copy or swap by the buffer ages stuff that I'm sending back, and so I can just copy as needed. I'm running out of time, aren't I? What?
You've got another 7 minutes.
Another 7 minutes, awesome. Okay. So here's how that's going to work. It's pretty simple. You take the old application window buffer and the application back buffer and you copy them together. That's how it used to work. And now here's how it's going to work. I'm going to allocate a window buffer that's big enough. It's going to have this little spare space around it. I'm going to paint the window manager decorations instead of the application contents. That should be faster, right? Okay, how does file descriptor passing work? It's this lovely POSIX operation. Oh my God, the API is a disaster. Somebody should be shot. This would be one of those really nice places where it would be great to deprecate this functionality by breaking it and replacing it with something more competent. I recommend that technique to you. The only way you could send a file descriptor is to send it along with some data. You can't do a zero length write and send a bunch of file descriptors. I don't know if it's a requirement, because as far as I know, a zero length write is a no-op in POSIX. All I know is this is the reality.
This is the reality.
Yeah, so you have to send some data. The other thing is if your receiving application doesn't carefully manage to get all the file descriptors you've passed after you've read the data that was written along with them, then it just randomly closes those file descriptors. So you have to carefully know how many file descriptors are possibly going to be sent to you so that you don't drop any on the floor. So, yeah, you probably can never call read or receive because those always close all the file descriptors they're passing over. It kind of sucks. You always have to call receive message because you're going to drop them. And more importantly, as I said, the sender and receiver have to agree on the maximum number of file descriptors that are going to be passed in any one write operation. Now, fortunately, the kernel kind of puts these little barriers between everything that has a file descriptor, so it won't merge reads across different groups of file descriptors. So a single limit is sufficient. You know that a receive message cannot receive more than the maximum number that the sender will ever send in one operation. So at least we're good there. We don't have an unbounded problem. So how are we going to do this in X? I'm only going to do it for requests and replies. You saw the previous stuff. The only time I'm going to get objects information back from the X server is in a reply. The only time I'm going to send stuff to the X server is in a request. So errors and events are not going to be able to do file descriptor passing. Now, we could add that, but the practicality I don't need it, and I think it makes it too complicated. I'm going to steal the second byte in the reply to mark the number of file descriptors so that the library can say, oh, when I get a reply, if that reply might have some file descriptors, then I can tell how many were sent by looking at byte number 1. Pretty simple. That allows for the sender to not know how many are coming, and for that information to come from the X server, and for the library to be able to collect them. Because inside the X library on the client side, all the replies are gathered. They have to be gathered, in series, but the actual library calls can come out of series. So we have to be able to suck the replies and stash them away, and that's going to include file descriptors. So I need some standard place to mark that. I could have had some magic callback sequence where they would have a little callback function to call and ask me, here's your reply, how many descriptors do you have? I decided to do it simpler. So in Xtrans, this is a lovely library that was invented, oh my God, yeah, for all the wrong reasons. So I'm just adding a couple of calls there. You can send a file descriptor, you can receive a file descriptor. Sending it doesn't actually send it, of course, because you have to send data with it. It just puts it in a queue. If the queue is full, as in there's more than can be legally sent in a single write operation, then you get an I don't know, there's some error return. E again, probably. And then the server is just going to flush the file descriptor to get rid of any queued, flush the existing data to get rid of any queued file descriptors and do the send FD again. So it should work pretty well. I also had to hack the client side, the XCB library. This was a lot easier and a lot more fun, of course. Thank you, Jamie. So I'm just adding possible file descriptor parameters to requests and replies. So I can say in a request, oh, this is not an integer that is encoded in the wire. This is a file descriptor. And so the request thunk just generates these calls to queue the file descriptors, and then it actually sends the request. Very simple. Very much like Xtrans, but a lot cleaner. And the other thing I'm going to do is in the reply, there's a special function that you call to get all of the file descriptors from the reply. So you get the reply, and then you hand the reply to this function and says, oh, you want 3 file descriptors? Yeah, I've got those, and it hands you the 3 file descriptors. So I think it works pretty well. This will obviously get reviewed. This is not final. So what I actually did is I went ahead and implemented file descriptor passing for the venerable MIT shum extension, because this is way easier than doing DOI 3000, and I thought it would be a good place to get some experience with this technique before we went and did a bunch more work. The other thing is that the MIT shum extension uses the System 5 shared memory extension, shared memory APIs in the kernel, which are kind of a disaster because, again, they use global names. The global names can be used by anybody, so we have all these security problems with those. So this actually solves a real problem. There are a lot of applications using this extension today to increase performance with the X server. So this is actually not just a demo. This is actually, I think, going to be a useful thing. I did 2 things. You can allocate a pile of memory on the client side to pass it to the server. You can also ask the server to allocate a pile of memory for you and pass it back to you. That's because I had to test both requests and replies. So everything that I've shown here is working, at least on this machine. I'm hoping to obviously get it cleaned up and reviewed and get it, hope to get it into X server 1.15. I have 2 minutes. Oh man. Intel Graphics has a page table for all of its graphics operations. We actually have two of them. Actually, we have n of them. One of them for scan out and one of them for rendering operations. They're fairly cheap to write. It's a write combining write. There's no magic flushing you have to do. You don't have to do inter-processor synchronization operations. You don't have the TLB flush is a relatively cheap operation. The other thing is the graphics memory is tiled. I have some pictures of that. Where is that? Let me show you the fun. I'm going to show you the fun picture of tiled stuff. So here's how the frame buffer actually looks on your screen. No, your screen is usually larger than this. Each page is one of these little rectangles. So it's a 8 pixel by 128 byte pixel. They're kind of fun. So we're going to hack the page tables. Instead of copying memory, I'm just going to swap the page table entries. Now that means I have to make sure that the images are aligned. You'll note in this picture, that application is not page aligned, the contents of it. So we're going to have to make sure the application is drawn at the right places in the pages. I'm going to do that by just allocating its back buffer page aligned. Right? This is smaller than this. You can see there's extra pages here that are on the frame buffer, but the page alignment is the same. So I can swap these pages into the scan out buffer just by doing page table tricks and not actually blitting the pixels. So here's the plan that I've implemented. Expose an ioctl to just exchange a rectangular area of pages between two objects, two of these graphics objects. Then you align the source rendering so the tiles all match. And then I can fill in the data in the surrounding area. Right? I can just fill in that from, just like we did with the window manager borders. And then I just rewrite the page table during vblank. So I get a vblank synchronized update of my sub-window contents for free. There's no blocking, there's no stalling. I don't have to do a copy, which is even better than we had today. I'm going to show you the status for that. The kernel ioctl is implemented. I'm sure Dave will just take it. He takes all this stuff. There's no alignment checks right now, so you get some amusing stuff on the screen. I'd love to show you a demo. But what I got was some really interesting performance numbers. It was way better than I expected. To do the copy pixels for a window that almost covers my screen is 300 frames a second with the application. To do the swap pages, I got 534 frames a second. But to skip the swap entirely, just keep painting the same back buffer and not do anything, was 730 frames a second. So I'm like halfway, more than halfway, from the copy to doing nothing. So things are doing pretty good. So that's what we're going to do for DRI 3000. We'll clean up the swap pages API, and I'll just push that right to Linus and bypass Dave so I don't have to do that horrible review part. Hack Mesa to support that over allocation and finish up the DRI 3000 extension protocol. And of course, we'll always profit from all these changes. Thanks for coming today. I'm sorry I ran over a little bit.
We still have a few minutes for some questions. Just raise your hand and I'll bring the microphone over to you. Right at the back first, of course.
It's good for your exercise.
How is all this going to help Remote X?
This is all direct rendering. Right? The Remote X I don't really care about. In Remote X, you're copying the pixels anyhow, sending them over a network protocol. And those network guys, you know, they copy all the time. Just stop doing that. Yeah, DMA. Hey, Willie's got a great plan. Yeah, do RDMA, and then you can just DMA the bits across the network.
Any other questions?
Airly does. Oh, there's one up there. And then Dave does.
So you said that you can't fix tearing on Sandy Bridge and Ivy Bridge. Is that actually true?
I can't do what?
Fix tearing?
This will fix tearing on Sandy Bridge and Ivy Bridge.
Ah, okay.
Yes, I can, but it will take this kind of software. And then Airly D had a question. And can somebody up in the upper corner think of a question? I feel like tennis. Over here.
When you're doing the resize, is there any reason you just wouldn't blit, you know, when you're doing a blit, just resize the whole thing? You know, just
scale it?
Scale it, yeah, rather than fill it in with crap or like empty crap.
We can do whatever we want. Yeah, we can do that too.
I think we have time for one more.
But we have no more questions.
How will this work with GPUs that have their own memory address space?
That's going to. We can do that over allocation part to do the window manager frame to fix the performance problems with window manager frames, and that gets us to parity with any window system that paints its own window managers. So we eliminate the performance cost of an external window manager. We just don't get to take advantage of reducing the cost of the partial screen updates. So we're still going to have to do copies for those. So we get, and of course the DRI 3000 changes will still fix a lot of the security and resize issues that we have. So we're going to get the benefits of that extension in terms of functionality and appearance. We just aren't going to get that final page swapping hack to reduce the copying onto the screen. So we'll reduce one of the copies, but not all of them. Thanks for coming, guys. Enjoy the rest of the day today, and I'll see you at the closing session this afternoon.